Hello, this is the first video of the series of videos where I'll be going through the summary questions for the AQA Physics A Nelson Thornes textbook. This is the AS questions, and we're going to start with summary questions from section 1.1. Okay, question 1. Part A asks us to state the number of protons and number of neutrons in nucleuses of several different elements. The first one is a carbon atom, carbon 12 and 6. We're looking to use the idea that's in the book of atomic number and number of protons. So atomic number being the nucleon number, or the number of nucleon particles in there, i.e. protons and neutrons added together. And Z being the number of protons. So in this case, protons is the simple one, protons is 6, neutrons, well, 6 plus another 6 would give us 12. That's I is an oxygen atom, and again protons and neutrons. Protons is easy, again it's 8, and neutrons is easy again, 8. 8 and 8 would give us 16. Very simple questions really. A little bit more complicated this one I suppose. Uranium, but the process is the same. So the bottom number here, the smaller number, it'll always be smaller, is a number of protons. Just write it down a little bit so I don't get mixed up with that. 92. And then neutrons, well, it'll be 235 minus 92, which is 143. And 2 more. Again, very simple. Protons is 11, neutrons will be 24 minus 11, so it's 13, and lastly it's 63 and 29, and that would be 29, and 63 minus 29 would be 34. Part B of question 1. So it's part B. It asks us a question about specific charge. It wants to know which of the above nuclei, so that's these, has the smallest specific charge for part 1, so that's smallest, and for part 2, largest. Okay. Now, what is specific charge? I'm going to go through this in a little bit of detail, far more than's probably needed to answer the question, but quite a few people have trouble with this, so we'll go through it quickly and understand everything about it. Specific charge is charge over mass. That's how we calculate it. It's just a ratio really. We need to add some values in here. The mass of an electron is 9.11 times 10 to the minus 31 kilograms. The mass of a proton is 1.67 times 10 to the minus 27 kilograms. The mass of a neutron is approximately equal to the mass of a proton. There is a slight difference, but in the numbers that we're talking here it will make absolutely no difference, so we can just consider them equal. Charge wise, well, the charge in the electron is 1.6 times 10 to the minus 19 coulombs, and the charge on the proton is also the same value, although it's different in polarity, it's the same value. There is no charge on the neutron, so that's quite easy. The specific charge on an electron, if you just an electron on its own, is the highest value you can get, and that's 1.76 times 10 to the 11 kilograms. Now it makes, coulombs per kilogram. Now that makes sense because the electron has the same charge as a proton, but a much, much smaller mass. Therefore, the number it's being divided by, so you've got a value here being divided by this value, the number you're dividing it by is smaller, and if you divide it by a smaller number, you get a bigger number out. So the smaller this is, the larger the number you get out. Therefore, for the smallest mass particle, we get the largest specific charge. So specific charge on an electron. Specific charge on a proton, that works out as 9.58 times, there's a point there, sorry, 10 to the 7 coulombs per kilogram. In the book it actually states that that's the charge, specific charge of a helium nucleus, but obviously a helium nucleus is just a proton, a single proton. The specific charge of a neutron, well, that's a tricky one. If you think about it, it has a mass here, but the charge is 0, and 0 divided by a number doesn't work. How does that work out then? Does that mean we ignore it? Well, no, because it does have mass. What it means is that there's no point calculating the specific charge of a particle that has no charge, and therefore we just would never do this calculation for a neutron on its own. But, and this is very important, we must consider neutrons when we look at specific charges of nucleuses or any combinations of particles where one particle has some charge. Even though the neutron isn't going to add charge, it will add mass and therefore must be considered. So we can't give a specific charge for it down here, but we can say that we do consider it in our calculations. So if we look at a specific charge, we could take the carbon one as an example, but we'll just go in general terms. The specific charge, well, you're going to have to calculate charge over mass. Now, we're only looking at a nucleus in this case, therefore electrons aren't going to be at play here. So we're going to be looking at the charge is all going to come from protons. There's no electrons, all going to come from protons. So the charge value is, well, doesn't really matter actually if it's protons or protons or electrons. The charge value is always going to be a multiple of 1.6 times 10 to the minus 19. What are we going to multiply by? Well, what has the charge is the protons. Therefore, the more protons, the more charge. Therefore, what goes here is the number of protons. Or we could write that as Z actually. We'll keep it in the terms we used here. So we'll call that Z. On the bottom, we're looking at the mass. Now, the mass in the nucleus all comes from the nucleons. In this case, it's important, as we said, to remember protons and neutrons. They both have the same mass, and therefore, again, it's going to always be multiples of the same number. 1.67 times 10 to the minus 27, which I've got from here. So, it's going to be multiples, how many nucleons there are, of this value. And the number the letter we associate with how many nucleons there are is A, which is up here. Now what we can do, again this is possibly in more detail than is needed to answer this question, but it helps us get our head around it. We can do a little bit of maths. We can split this fraction because we've got a times and a times above each other. And we can say that in general terms, the specific charge is going to be Z over A times this part. 1.6 times 10 to the minus 19 over 1.67 times 10 to the minus 27. And when we actually do that calculation, we find that that value works out at 9.58 times 10 to the 7. Now, this value will never change. If we're just looking at nucleuses of atoms, obviously if we had electrons involved it's a little bit more complicated, but we're just looking at nucleuses of atoms here, this number will never change. And therefore this is a constant. So what number you get out in the end for specific charge is determined by what number you times the constant by. The bigger the number we times the constant by, the bigger number we get out. The smaller this number here that we times the constant by, the smaller we get out. If we get a number that's less than 1 here, we'll get a number out that's less than this value. So let's have a look at this in a little bit more detail. Let me just move the paper up. So, we have a situation where we have Z over A. Now Z, let's look at this in terms of protons and neutrons. We can say Z is the number of protons, A is the number of protons plus the number of neutrons. And we have a situation here of P over P plus N. Anyone who is really good with maths will sort of see the relationship developing here, but just to give you an example of how this relationship works, we can put in a couple of test values. If we look at, we're concerned really with N in this case. If we said that N was equal to 0, what would happen? Well, you'd have P plus 0, which will just be P, so you'd end up with P over P, which would be 1. If N is any number above 0, so we can just use 1, it's the easiest thing to do, then P is divided by P plus 1. Or if this was just N, you give it a random value N, it would be P plus N. Now, that means the number here is going to be divided by a number that's just slightly bigger than that number, and that's always going to give you an answer. The number you get out of that is always going to be slightly less than 1. Depending on how big this number, it could be a lot less than 1, but at this point here, just N is 1, it'll be slightly less than 1, but it will definitely be less than 1. And the last thing we can look at is, what about if N approaches infinity? I.e., what if N becomes very, very, very big? And then you have P over P plus infinity, or a big number, and that means this is going to become huge compared to this, and that means that this is going to become almost 0. So you can see that depending on the value of N, we could get a number out for this ratio that's somewhere between 0 and 1. It would get a 1 out if N was 0. If N was very, very big, we're going to get a number very equal to 0. And anywhere in between, we're going to have a number less than 1. So the ratio of protons to neutrons is what's going to control this answer. Which means that we also, coming back to answering the question, you can look for a situation where the number of protons is high compared to the number of neutrons. So, if we actually work it out, we can see that for carbon or oxygen, because they both work out the same, because when you do this bit you get 6 over 12 or you get 8 over 16, both work out to be a half. So for carbon and oxygen you get 4.79. These are all times 10 to the 7 coulombs per kilogram. For uranium, we expect this to be small because very high proportion neutrons to protons, and it is 3.75. And then our last two, which aren't actually of interest to us for this question because they won't work out, 4.39 and 4.41 of any interest to us. When coming up to this kind of question in the exam, it's possible, this is all obviously way over the top, I just wanted everyone to understand exactly what's going on, but it would be possible to work this out simply by knowing that this will always be a constant. Rather than typing all the complicated numbers into a calculator, you can just work out the ratio between Z and A, and the biggest ratio will give you the biggest specific charge when you times out by that number. It doesn't ask you for the value. So, in an example, I could have worked out that uranium was the biggest by doing 92 divided by 235, and I don't know if you can see this on the screen, but it gives me 0.39. And if I looked at carbon or oxygen, it would have been a half. And these would be somewhere in between. So I could have just, all I had to do was just work out the ratio and that would tell me the answer. Bit of a complicated question, that. Easy if you understand specific charge very well, not so easy if you find it difficult. Let's move on. Part 2. It asks us to identify the following parts of an atom. So A is the part with zero charge. So the part with zero charge, that's easy, that's the neutron. I've already mentioned that above. B, it says the part that has the largest specific charge. Well, we looked at that up here, and it's always going to be the electron because it has the same charge but much smaller mass. And part C, the number that the particle that when removed gives a different isotope, and again that's neutrons, and we should remember from GCSE that neutrons control isotope. Okay, question 3. My page right up. Question 3 says we have an atom that loses 2 electrons. Gives us the numbers for the atom, and because it's lost 2 electrons we could call it plus 2. Okay, obviously electron adds a -1, so if we take 2 -1s away it's equivalent of leaving it plus 2, and it's formed an ion. Now, we have drawn that ion here, so I've taken the important information from the question. First of all, it says calculate its charge in coulombs. Now this is incredibly simple. You should not need to go to any extraordinary lengths here. Okay? The reason is the charge is just 2, and what do we times it by to get coulombs? Well, we times it by the charge of an electron here. So we're looking at 2 times 1.9 times 10 to 1.6 times 10 to the minus 19, and you'll get 3.2 times 10 to the minus 19 coulombs. So that's its charge. And we know its charge determined by the number of electrons that have left in this case, and it's always going to be multiples of 1.6 times 10 to the minus 19. Nice simple bit to start. Part B. It asks us, state the number of nucleons it contains. Again, easy question. We know that the number of protons is 29, so the number of nucleons is protons and nucleons added together. That's given to us as well. So the nucleon number is 63. So the number of nucleons it contains is 63. Not even have to do a calculation there. That easy. Okay, part C. Here's where it gets a bit more confusing, I suppose. To calculate the specific charge in coulombs per kilogram. Okay, so specific charge we set up above is charge over mass. What's the charge? Well, the charge is there. No point even putting the times and all that in. Why bother? We've calculated it. That is the charge of the atom. Remember, bear in mind here, and this is really important to pick up on, look through the question. Is it talking about nucleus or the whole atom? Up here, it was simple. It was just talking about nucleuses. Okay? Down here, we're actually now looking at whole atoms. So that changes things a little bit. The charge is now no longer how many charge-carrying particles there are, because some of them charge-carrying particles are counteracted by opposite polarity charge-carrying particles, i.e., in more real words, some protons' value is cancelled out by electrons' value. But we know this. We know this when we looked at it here and we said this was +2. We knew we'd already done the maths of what was left. So it's just a slight extension of what we would already come to understand. So we know here the difference in charge will be +2, which will give us 3.2 times 10 to the minus 19. The mass, well, first of all, we've got the mass of the nucleons, which is 63, so 63 nucleons, times 1.67 times 10 to the minus 27. Now, do we need to consider the mass of the electrons? Well, this is a bit of a tricky point. Mathematically, no, but for a physics point of view, yes. They are there, they are adding mass, and therefore if you're considering how it works and you're trying to get your mind around what's going on, yes, they are there, they do add mass. But mathematically, their mass is so small in comparison to the mass of a proton that they will, if you even go to the trouble of adding the electrons in, it's not going to make a difference to the result you get. It may change it the 6th or 7th decimal place, but at that point you're going to round up and you're not actually going to see it. So yes, we should theoretically add the value for the electron mass to it, which would be 29 minus 2, so it'd be 27 times 9.11 times 10 to the minus 31. Put that here, add it to here to get a total, but if we did it, we'd find it would make absolutely no difference. It's such a small value, it's not going to matter. And therefore we just use this and we get an answer 3.04 times 10 to the 6 coulombs per kilogram. Okay, lastly, to turn over, we're going to look at question 4. Question 4 asks us to calculate the mass of an ion that has a specific charge of 1.20 times 10 to the 7 coulombs per kilogram, and has a negative charge of 3.2 times 10 to the minus 19 coulombs. Now, the negative charge, well, it doesn't really make a difference in this case because we're looking at the value, the number, not really the polarity. So it's just the negative is just going to tell us that the difference comes from having more electrons than protons rather than having more protons than electrons. Specific charge, easy to work out. Let's do it here. Charge over mass. And I do recommend, write out every time, make sure you know what you're calculating. Specific charge is charge over mass. Charge in this case 3.2 times 10 to the minus 19, and the mass, well, we don't know, and that's what we've got to work out. So we need to do a little bit of rearranging so we can get what we want, because we do know this value, so we can calculate, we can do a bit of swapping round, and we can say this is true. Well, we can times by mass and then divide by that, but in essence we're going to swap. We can swap these two terms. So we find that mass is equal to charge over specific charge. Okay, so mathematically you can do the algebra, but you can bring that over and it ends up down here, and you can take this over and it ends up there. Okay, so we've got this new one. Now we're putting our figures, it should work. We've got charge 3.2 times 10 to the minus 19 over specific charge of 1.20 times 10 to the 7, and we get an answer out that is 2.67 times 10 to the minus 26 kilograms. part B says the ion has 8 protons. In the nucleus, how many neutrons and how many electrons does it have? So, easiest one to do first, well, we want neutrons and we want electrons. Easiest one to do first is electrons, because we just said the fact that it's minus tells us where the extra charge is coming from. Extra minus charge is going to come from extra electrons. There's 2 lots of 1.6 here, because we know that. We've done that calculation so many times, we know that 3.2 is double 1.6, but you could work it out, divide by 1.6 and it will give you 2. So we know there's 2 extra electrons, which means there must be 10 electrons. Neutrons, well, we know the mass, and we know that most of the mass, or mathematically all of the mass, is going to come from the nucleus, is going to come from the nucleons, the protons and neutrons added together. Therefore, the mass of the nucleus is equal to this. Yeah. So, if we want to work out how many there are, we need to divide by what 1 is. So we could say 2.67 times 10 to the minus 26, and divide that by the value of what 1 nucleon is, and that should tell us how many nucleons make up that value. 1.67 times 10 to the minus 27. When we do that, you get an answer out which is 15.98, so we can see it's slightly got a little bit awry here, but that would just be in the rounding. Theoretically, that's going to be 16 nucleons. If we know there's 16 nucleons, we know there's 8 protons. 16 minus 8 will give us 8, and therefore we know there must be 8 neutrons. That's the end of the first summary questions. Thank you very much.